And then in the end, they have all these candidates, and they, as I've said, use the emulation and see does it actually execute to read all these many false positives you would get on any data. libemu is written by Markus Kötter, is one of the implementations of this approaches. There has been a lot of papers and surprisingly little actual implementations available to the public. libemu is actually being used in a lot of projects, I think. The client-side honeypots from the Honeynet project, PhonyC uses it, Diamnia and Nepenthes and wCollectD use it, so it's pretty widespread in use. So meet libsizzle. I was looking for a nice library name. libshellcode was taken, libcpu was taken. SC is usually short for shellcode, so I called it libsizzle. So the way libsizzle works is basically it builds up on this getPC primitive a little bit. So it uses these possible getPC sequences to find candidates of shellcode start as well, to minimize the amount of data that is being looked at. But since we have a higher grade of performance, we can be less strict. So we're allowing a little bit more of these getPC sequences to trigger. We don't do so much verification, and we hope to catch more actually shellcode with that. And instead of building up this huge tree of possible previous locations, we just take a window around these getPC sequences and brute force every byte as possible starting offset. Again, which is possible due to the performance and efficient emulation. So, for example, I don't know actually the limits of libemu where it stops building up the tree, but usually it will not create so many previous bytes because the tree grows very wide, very fast. Or it's actually even a graph, but we can call it a tree. And so in this case, we just save this overhead by brute forcing over every possible byte location. And to actually do this efficiently, we have to do some hardware accelerated execution. So we need to actually execute these possible shellcodes on the native CPU, which is another limitation of this approach. You can only detect x86 shellcode on an x86 machine. However, we're not using any of these virtualization techniques like Intel VT or other like binary rewriting, stuff like this, because it's too much overhead, it involves context switches and so on, and we have too many candidates. We would be pushing on the native CPU for switching to a hypervisor all the time and back. However, we still want to have some security such that our detection machine cannot be truly owned because we executed our own process, the malicious shellcode. libsizzle is available on the URL there. However, I don't have the latest code there. I need to push it. So how do we achieve this separation, this execution of code? Most people are familiar with paging on the x86 architecture. For those who are not, it's very simple. You have so-called pages, which are usually 4 kilobyte blocks of physical random access memory, which is depicted here. And the virtual address space of a process doesn't have anything to do with the real physical addresses. Instead, there are tables that map each of these 4 kilobyte blocks to the physical memory. So you can have arbitrary mappings. As you can see, 2 virtual pages can even be mapped to the same physical memory, or some virtual pages are not mapped at all. That will generate an access violation if you access them. However, there's another thing on the x86 architecture, which is segmentation. Segmentation comes from the really old days where programs, where memory was sparse, you didn't have the operating system protections like protected mode yet, and so on. And a memory segment was, well, you still have segments and binaries like a data segment and so on. They're called sections these days to differentiate from segments, but that's where it really originates from. And a segment is basically a view of the virtual memory. You don't see that in modern operating systems usually, because a segment on a modern operating system starts at address 0 and adds at address 2 gigabytes. So usually segments are as big as the memory you can see. However, the CPUs, at least in the 32-bit mode, they still have the segmentation support in hardware. So what we can actually now do is, instead of using a segment to map all of the virtual memory, we can create a segment which only maps a part of the virtual memory. So the trick here is that for memory isolation of the code that we're going to execute, we're going to create our own segment that we're going to switch into that only allows this shellcode to access the memory within that segment. So the shellcode can actually not modify or see or whatsoever our memory of our analysis processes. Will only see the segment memory. And segment, so the shellcode's address 0 where will actually be where the segment stops. So this is actually what the shellcode will see. It's just a window of the memory, and this is our real process memory, which is then backed by the physical memory. And there's a processor feature, which is a local descriptor table, which allows us as a userland process, with a little bit help from the operating system, to actually create these segments and use them. So now that we have these segments, how do we execute code or emulate code in a safe fashion? The guest code that we're going to execute or emulate it is disassembled. So we need to look at the code actually. Okay, thank you. And we need to stop this disassembly at every potentially harmful instructions. These are either privileged instructions that would trigger a privileged instruction exception, like access of operating system-specific registers and so on, or any instruction that modify the execution flow. Because we do a linear disassembly, we cannot predict indirect calls, indirect jumps, or something like this. So everything that somehow modifies the execution flow also stops our disassembly. And this means our disassembly runs are roughly equivalent to basic blocks, as you might know them from IDA Pro or other static analysis approaches. So we also consider any access to a segment register. These are the registers that tell the CPU, okay, I'm currently dealing with this segment, as a privileged instructions, even though they're not privileged instructions in the x86 architecture. And that is simply because we use segments for protecting ourselves. So in case a shellcode would modify a segment register, it would gain memory access to our host process memory. So we consider it privileged as well. And then what we do is we execute one basic block at a time on the host CPU and inside the separated segmented memory. And we emulate all other instructions, like privileged instructions, the segment register accessing instructions, call flow, or instruction flow modifying instructions in software. But this is still a huge benefit because most of the code is not such instructions. And yeah, we have one exception, that is backwards short jumps that we will see in loops. What looks like this in IDA. This will not, if it's predictable where the jump is going and we know this is actually going into the same basic block we're already executing, we will not put this into a new basic block and execute it directly on the CPU. Most loops that you actually do encounter, due to the way compilers work, due to the way manual shellcoders design their shellcode, are designed in this backward fashion. So you have some code, and then you have some counter check, and then you jump back, or you continue the execution flow. And that means that we can actually accelerate most of the loops, especially XOR, decoder loops, or whatsoever you will run into with this approach very efficiently. So that means every decoder loop will just be put on the host CPU, executed, takes a couple of nanoseconds on modern CPUs to do the decoding and so on. Very efficient, very fast. So, 2 evaluation slides of the solution. Unfortunately, I cannot do a demo due to the short time slot, but yeah, here's the output from running the binary that belongs to the library on 32 megabytes of random data, and it takes about 300 milliseconds to analyze these 32 megabytes of random data. Random data is really the worst case scenario because we have more getPC sequences than we would see in normal normal data if you would look at HTTP or whatsoever. Unless you have images maybe in there, you would usually not see a single getPC instruction. But we assume the worst case here. So yeah, this is what I did just last night. So this means we can do about 100 megabyte a second, which is 795 megabit a second on a single core on my presentation laptop here. So that means if I would use 2 of my 4 cores for shellcode analysis and maybe another core of these 4 cores for stream reassembly, I could actually do protect the gigabit network stream with just this laptop here. And on a commodity server, of course, you can protect the 10 megabit university uplink or whatsoever. Actually, our university has a lot more, but here you have 2.5, I think. So, so at least you could here protect this facility here. And this is actually a factor 1,000 faster than libemu, which is a kind of an unfair comparison since libemu is a software emulator and this one is hardware accelerated. But yeah, this is just, you can just plug it in for shellcode detection. Okay, thank you. And real world data, as I've said, is usually faster than this purely random data. So it's fast, but doesn't actually work. What's the success rate? Well, false positive is basically none. Because if it's detected, it successfully ran as bytecode on the host CPU, and I have metrics like it executed at least that many instructions, that many basic blocks, and so on. And yeah, if it's detected, it at least resembles valid shellcode. And then you get kind of into a philosophical problem. If you have random data that is also a valid shellcode, is it really random data or is it a shellcode? I mean, so that's why I say it's no false positives. You could theoretically, of course, generate random data so long until you get shellcode, but yeah, then you have shellcode. And then false negatives, none so far. Manual evasion is, of course, possible if you know the approach, because, as I've said, I'm using getPC sequences, and if you would get around these getPC sequences in specific cases, you would not detect it. However, that even in the targeted attacks I've analyzed, like Operation Night Dragging or the recent DDoS attacks in Korea, you always have these getPC sequences in shellcode. Nobody really writes a shellcode in such a sophisticated way. Actually, here on the side, you see a little bit more sophisticated shellcode than the normal shellcode. Instead of a not instruction, it uses some other FPU instruction, which loads the logarithm to the base of 2 of the E constant. You probably know that from math. It has some decoy instructions in there. It uses a large SIP-based operand actually here, stores 4 bytes at a time, it rotates the key and so on, and it uses a little bit other loop mechanism, and still that one is easily detected. I've tested it on a lot of public shellcodes, like what you see on the tricky metasploit ones, like the alphanumerically encoded ones, on some egg hunter shellcodes, which are very, very small shellcodes, and so on. And also I've used this during CTFs. So we play CTFs regularly. Of course we didn't actually use it and drop packets that contain shellcode because that would be cheating. But we recorded the traffic and we looked if actually we would detect the shellcode. It worked for DEFCON, which is a high profile CTF. It worked for RU CTF, which is just nice CTF. So in the real world it pretty much works, but I can circumvent it, and I bet others can too. So, but that's really, that is really if people would know that this is in place and they need to do a targeted attack and get around that, then it might be possible. But on the real world, it's for like honeypot applications, it's really, really feasible. Any questions? I know this has been deeply technical. I'm around all day, and if you have questions, feel free to just walk up on me and ask me anything. Okay, thanks for your attention.